Okay, so as the chair introduced me, I'm Syed Islam. I'm from Curtin University in Australia, and it is my great pleasure to be here, to be able to stand in front of you and give this talk. Over the last couple of days, we are hearing a lot of development in power electronics and in the inverter-converter sides. We are also speaking on, of course, applications in the area of renewable energy, and that is very important. And where I am going to take you in this talk a little bit is where the renewable energy and the power systems, they actually interface. It's very important that when we bring renewable energy systems onto the grid, as we know that renewable energy is a very intermittent source, and they could vary very widely, and they could pose serious threat and challenges to the grid. And it is extremely important that the grid operators are able to manage those challenges if renewable has any future in commercial grid. We could do a lot of work in the laboratory, but when it comes to utility and accepting technology, we need to convince them that the technology that we have are actually able to satisfy the requirement for the grid operators. So what I'm going to try to do is show you some of those challenges, some of the requirements and needs. So when we work on converter-inverter technologies, topologies, we could keep those in our mind. And I show you some of our own research work and how we have tried to address some of those. So let me just get it right. Okay. Right. This is going to be outline of my presentation. I'm going to talk about a little bit on variable power generation and the status in the world right now. I'm going to talk about a little bit on international grid codes, and that's where the utilities is concerned that I'm going to bring into you. I'm going to talk about mainly on wind. So I'm going to talk about wind energy conversion systems and the various types of them. I'm also going to show you some work that we have done with the Horizon Power, one of our local utility, which serves the remote area system, and some of the example there in solar smoothing. So we'll be able to appreciate some of these grid code issues. And then I'm going to just show you a little bit on the enabling technologies that we have worked on, and some issues in relation to the wind turbines drivetrain and its monitoring, and draw a couple of conclusions. So the variable power generation, whether it is wind or it is PV, they are on the rise. Now many countries have set very ambitious growth target on variable power generation. For example, EESA estimates, the Department of Energy in US estimates that they could actually have 80% variable power in their grid by 2030. This is called the project P2030. Now, whether that's going to happen or not, theoretically it is possible, but I think there are many challenges that they know. Australia, our own country, they also have ambitious targets. So we had a target of 20% by 2020. Our opposition leader, he is more aggressive on renewable. He wants a bigger share of renewable into our grid. And many countries around the world, I'm pretty sure Chile has got similar ambitions that they would like certain percentage of renewable coming onto the grid. So where do we stand today? In 2015, we had about 432,000 megawatts of wind power installed in the world. And as we speak, in 2017, in 1 year time, okay, this number have gone many, many megawatts, thousands megawatt more. People now putting in very large wind farms. Those are thousands of megawatts. In 2014, the global PV installation was 178,000 megawatts. However, when you look at this number, and in terms of the world's energy need, where we are? Well, in 2015, according to the World Energy Research Center, what they are saying is that still we draw 76.3% of our energy from conventional sources. That's mainly coming from coal, thermal, and nuclear, and so on. However, we had in 2015 about 24% of all power generated from renewable sources. When you drill down a bit further more, you see that out of that 24% or so, about 16.5% comes from hydro. And no wonder that there are some countries in the world very blessed with the hydro resources, and they have got very large hydro plants. So yesterday we heard from our Paraguayan friends who said that, in the Itau project, they have got like 14,000 megawatts worth of hydro. In China's Three Gorges Dam, they have got 18,000 megawatts worth of hydro. Okay, Australia is not so lucky, and we have got very limited amount of hydro in our system. But when you look at that renewable mix, you see that only about 3.5 to 4% is wind. So much wind we just saw, but still a long way to go in terms of large-scale wind farms and them coming into meeting our energy demand. When it comes to PV, it's even smaller. Only 1.2% in 2015 was coming from PV. And about 2% coming from biomass and 0.4% from geothermal and others. So I talk about Australia. So this is Australian scenario. You notice here that in Australia, in around 1992-93, okay, whatever hydro we have, we actually did not change much because we don't have much hydro source. Okay, in fact, during this 2007-8 period, we actually had our hydro production went down, right? But what is happening is that slowly and surely we are having increasing penetration of renewable sources into our grid. So much so that in the year 2013-14, we generated as much from renewable that we used to generate from hydro. Now, if we have this figure reproduced today, this has gone much farther than that. As a matter of fact, some of our states, like South Australia, are now producing or capable of producing up to 80% of their energy coming from wind and solar. Some states in Australia are more aggressive than others, and we have got now very degree of penetration into our grid. Around the world, same thing is happening. If you look at the USA situation, this figure is known as the dark curve because it looks like almost a dark, right? And what it is that basically it is from the Californian Independent System Operator, and they are predicting that by the year 2020, what is going to happen to their load curve. So if you look into that load curve, you actually basically seeing that by the year 2020, during midday, okay, because California has mainly PV plants. So during midday, there will be that much power generation that will be coming from photovoltaic and other renewables, mainly photovoltaics, and huge conventional power that they used to generate is going to be replaced by renewables. So what is the problem with this? The problem is here, is that when this photovoltaic starts to disappear or the sun's insolation energy starts to reduce during the day, we are going to have a huge requirement of ramp power to meet the demand. And this can happen in the space of roughly 2 to 3 hours that you might need approximately 13,000 megawatt of energy that need to now come from alternative sources that so far was being generated by variable power. So this creates a huge challenge on the system operator, that how to manage this huge power balance. I also now draw an experience from our own utility. This is a utility, Horizon Power, and Western Australia, we have got our main grid, which runs about 1,000 kilometers, and then after 1,000 kilometers, which you could have another 2,000 kilometers, even still in the state of Western Australia, okay, you have to then generate your electricity from independent power sources. And this company, Horizon Power, runs autonomous power system, mainly remote area power systems. So, and they are located in different places. So this is a power system which is a place called Mabelba, and this system is composed of 250 kilowatt worth of centralized photovoltaics, and it has got 4 diesel engines, and it has got a 25 kilowatt hour of flywheel energy storage system. Okay? And its peak load is roughly around 580 kilowatts. So I'm now just going to show you here in this picture that what is happening. So if you look at this yellow trace, okay, that is the trace which is the PV power from that 250 kilowatt worth of PV. We have got good sunshine in our state, so therefore it was generating 250 kilowatt plant was almost generating 250 kilowatt when the sunshine was good. Now suddenly what happened, and if you look into, and I don't know and I apologize for these small fonts here, but as a matter of fact from here where the sunshine was 250 kilowatt and until here when the power, the PV power drops from 250 to less than 50 kilowatt, is only 36 to 39, 40 seconds. That's all it takes. So in about 40 seconds, you have lost PV from 250 kilowatt to 50 kilowatt, okay? And you have to now balance this power, because if you did not, what is going to happen? Okay? We will have a serious issue with our voltage and frequency, all right? So what is happening now here is, as you can see, is that is the demand. Of course, we have got no control on demand. People, determines what demand they have. So that's the demand. And unfortunately, when this cloud event happened, okay, the peak demand occurred. So as a result of that, what was happening is that diesel generator, okay, which was ramping up because this was online, so it was spinning. So it could now, its governor can sense that the frequency, which is on this curve, is actually has taken a dive, okay? Then delta omega over R, negative, what it is going to do, that's the droop control. What the governor is doing is basically pumping up power on the diesel generator. So the diesel generator started pumping power, okay? And then this diesel generator, which was basically idling on the system, at that point, it started to pick up power as well, and that diesel generator started now to bring its own output down. But see, because that diesel generator could not come in line until this time, right? The flywheel, which is this trace, okay? The flywheel energy storage system started to kick in, and then it was trying to take up the load and help the diesel generator and restore the voltage and the frequency. So that is the voltage trace, okay, which you see that eventually through some sharp transients, some undershoot and overshoots, it settles down around 1 per unit, and the frequency settles down approximately around 50 hertz. Okay, but this is what is going to happen. So now, when this thing has to go through, and you have storage system, okay, we have got bidirectional storage system. We design our bidirectional inverters, converters, right? The control system for that, they have to make sure that they are able and they are compatible with this grid requirements. All right? Now, the grid operator, if you are the PV plant operator, the grid operator is going to demand from the PV plant some of these ride-through capabilities, some of those solar smoothing capabilities. They have to ensure that they are able to provide that smoothing. So this is the system operator's job. As I mentioned to you, they are the one who will carefully balance the load and generation, including the variable power, together with the control of PV and any storage or wind that they may have. When we look into the renewable energy scenario in the world today, okay, and as we say that there is still a long way to go in terms of generating a sizable amount of power from renewable, okay, we need huge amount of renewable into the grid. The one that promises the major technology is actually the wind, okay, mainly because that wind cost per megawatt installed is very competitive these days. It's almost cheaper now than the peaking plants, some of the peaking plants, let alone the operational cost of the peaking plants. So what is happening also that the wind power, we have got now larger units available. So we are hoping that by the year 2020, we will have 20 megawatt of wind power plant, one wind turbine can generate up to 20 megawatts. And imagine what's going to be its blade diameter. Its blade diameter is going to be approximately 300 meters in diameter. It's huge, right? Monster. But we are going to have that. We're possibly going to put many of those in the offshore area and, of course, in the good wind where it prevails. But the fastest growing technique is going to be wind. So I'm going to now concentrate a little bit on the wind energy conversion systems. So when it comes to wind and those large wind turbines, okay, and we are designing the power conversion system, which is known as WEX, okay, there are few technologies that is available. So the four main technologies that is available in the wind power area. First of all is the top one that you can see in this figure, which is that basically is a fixed speed system known as a fixed speed system, and this technology is primarily through squirrel cage induction generator, and that is known as basically type A conversion system. I'm going to say a little bit more on the next slide on this, but just show you the pictures of these different conversion system. Type B is actually the similar as type A, except that type B uses the one rotor induction motors or induction generators. Type C is actually, again, they use the similar technology as the type B, which is the DFIG, known as the W-fed induction generators, okay? And that is the type C WEX conversion system, where this rotor side converter is approximately 30 to 35% of the total capacity of the turbine, and the rest is directly connected to the grid. Okay, I'm going to talk a little bit more on those in a couple of slides. Type D is again a similar wind energy conversion system, where this generator is primarily permanent magnet synchronous machines, and what it is that they use full converter to connect to the grid. So these are the main four types of wind energy conversion systems that we use in wind energy. Okay, so type A, which we just saw, what are the key features of these type A machines? Well, the type A, essentially what it is that they use the squirrel cage induction machines, and as you know that because of directly coupled to the grid, the ability for these type of conversion systems to control the speed is very, very limited. You could probably maintain the speed in the range of plus or minus 1 to 1.5% at the max. So that is where, so basically what it means that you have to have very good average wind speed for using this type A technology for wind power generation. Okay, else if the wind power drops, then wind speed drops, then you basically have to disconnect the wind turbine. This type of machine, type A machines, one of the thing is that because they are induction motor, induction generator, they are very much dependent, their torque and power output, on the voltage level at the terminal. So the power is basically proportional to the V square. So therefore what it is that they are vulnerable to system faults. When system faults happen and then your terminal voltage go down, then this power transfer capability of them also seriously impacted. We will see them a little bit later as well more. Soft starter is needed because induction generators, induction motors, they demand serious current during start. So you need soft starter for them. And because of the reactive power requirement of these type A machines, you need STATCOMs or large scale capacitor banks to supply their reactive power demand. And their aerodynamics and their power output can be controlled using a stall pitch and active stall, active pitch type of control. Type B wicks, which is the one rotor induction motors or one rotor induction generator technology, basically is a bit better than the induction generator. Their speed could be controlled. Their speed could be controlled up to 10%. So I'm given some warning here. So I'm going to move a little bit more faster. Type C machines, on the other hand, as I mentioned, that they use the rotor side and the grid side converter technology, and basically because of those technology, you have got better control on active and reactive power control of the wind power generation. Type D, on the other hand, which is the variable speed machine using the synchronous power magnet synchronous machine, they are probably the best which you can control active reactive power power factor of the power factor of connections to the grid. Okay, these are some of the key performance requirements that we need from the wind energy conversion system. All right, I think I've mentioned to you before that we need fault right-through requirements, active and reactive power control, extended variation range for the voltage and frequency, and inertial support, therefore, the active power control, the reactive power control, and maintaining efficiency. Now, when you have these wind farms and you want to connect it to the grid, the utilities will now around the world will demand that you meet some of those grid codes. And I'm just going to show you a few of those, right? So what it is that in this grid codes, okay, which is a Danish grid code incidentally, it actually says that if you have got your rated power and the voltage reduces to around 20%, okay, you could still stay connected up to that 0.5 seconds, but then the voltage has to recover to about 90% of the rated voltage, okay, unless it does, the wind farm will have to be disconnected. So what that basically means that the capability of the inverter and the converters will have to match this if you are willing to generate power and connect to the grid. So similar LVRT, this is known as the low voltage ride-through. This is the German requirement, and the Germans actually say that you could stay connected even it goes to 0 for about 0.15 seconds, but then it has to recover just like that. Okay? And then you have got the frequency and the power requirement, and that determined by that curve. Then you have got also high voltage ride-through, which is for voltage swells, not just sag, but voltage swell, and this is an Australian requirement. Then you have got the delta constraint or the delta ramping constraints, and that is basically for maintaining spinning reserve, and you have to maintain that curve when you are generating the wind power from wind energy conversion systems. Okay, those who will be designing the inertial control and the droop control for the inverters, okay, they have to look into that standard basically to maintain the droop ramp rate and when the droop controls are possible as a function of the voltage as well as power output of the machine and frequency. So all of these must be kept in mind if you're designing inverters for wind energy conversion system. Okay, so I'm not going to do the summary because of time. And I'm going to now basically show you some of the work that we have done. So this work was done basically for the defig machines in order to help the machine and maintain the requirement of the grid code using a simulated superconducting magnetic energy storage coil that will be used in the rotor side and the grid side converter. So essentially what it is that you can see that that's a wind farm, okay? And this is the defig machine. That's the rotor side converter, which basically controls the active and reactive power of this generator for the machine. And the grid side converter maintains the DC link voltage as well as controls the power factor and the reactive power requirement of the grid. Okay? We are designing a mesh system to help this to ride through when a fault happens on this at this point of the point of common coupling. So what it is that this is the control of that rotor side converter, which is a current control, and this one is basically an intelligent control that is controlling this DC chopper mesh high temperature coil, and this is basically going to maintain the DC link voltage in case of system emergency. So what it is that by doing so, we were able to, and you can see it here, that without this mesh coil, okay, the voltage could actually dip much further, but with this mesh coil, the voltage recovers much faster and it does not dip that much. So we believe that that is a better type of control that helps the inverter. Similar thing, that's the DC link voltage. You see that there is a lot of excursion and a lot of magnitude if you don't have the control, mesh control during the fault. And when you have this mesh control, you basically have not too much of transients, and that's a lot better for the DC link capacitors, so for its life and for the control of power. Okay, the other thing that I'm going to tell you and very quickly and then stop is that one of the major issues in the wind farm and wind energy conversion system is the gearbox. Okay, you need a gearbox if you have a variable speed machine, defig, or you have the induction machines. Okay, so what it is, the gearbox actually causes 59% of the fault in a wind energy conversion system. Okay, and that is a big issue because these gearboxes are top on in the tower and or on the offshore rigs, right? It's very difficult to maintain them, and you need to know, because when you have, it's just like PV system, when you have a PV panel and it has got dust on the top of it, your power production reduces dramatically. If you have a wind energy conversion system, okay, and if you have got a faulty gearbox, your wind power is actually going to drastically reduce. And unless you're monitoring it, you wouldn't know. So the effort now toward is online monitoring of these equipments, and particularly the gearbox. So this actually is showing that when you have a faulty gearbox, there's a lot of energy in that gear is being produced. When its situation becomes even worse, in one day you could produce probably same amount of energy because it is worst. And if you maintain that gear, then that energy in vibration reduces dramatically. Okay, so because of that, we actually assembled our own prototype defig system to study this instrumentation as shown in here. We did some signal processing, and this is for a good and healthy gearbox. You see the key dominant frequencies. When you have a faulty gearbox, you start to see a lot more, including the dominant frequencies, as sidebands. So what then you need to do is basically correlate them, and what we have done is part of a PhD project is that they have knocked the tooth at many places of the gear and then try to correlate these physical frequencies. So we can then look at these when we are online and display. The operators could tell that what is happening and how much damage, gear damage has taken place. So these are important things in wind energy conversion systems. Well, I think I basically tried to give you a little bit of an idea about the requirements for the grid and what it demands from power electronics, those who are designing them to meet those requirements. I tried to show you a little bit of wind energy conversion topologies and technologies. Because of time, I couldn't go into detail of them. I show some of the work that we have done and try to give you a little bit of a experience in the area of vibration through gearboxes and how you could monitor them, and some of the challenges and the solutions that people have in making it possible that in the future that we could actually have large amount of renewables penetrating into our grid. Thank you very much.